So I'm going to start with a motivating example. And again, I don't want to be the speaker of doom, but like all of these examples are disasters, unfortunately. But there's this thing in cognitive science that, the way we process ideas in our mind, an idea is more likely, there's different levels of storage in your brain. I am looking for deep storage to kind of plant ideas deeply in your brain so that they're there whenever you need to access them. There's deep storage, and then there's retrieval. With retrieval, that's what you do with your homework assignments and kind of questions and activities. So, but to access a deep storage, in your brain, you have to evoke emotion. Okay, so an idea is more likely to stick in your brain is if it makes you feel like so concerned about something or makes you very excited and happy, right? And so, but it just so happens that these examples I'm picking, they are unfortunately correlated with, unfortunate events, but they will have the same effect. Those events happened in reality, but they have the same effect of them hopefully sticking in your brain. So this example, so in the chapter on errors, we saw the example of the round of error. This one is an example of linear systems of equations and the need for linear solvers. Although it's not directly apparent, they never mention the word linear solvers, but I know that they use linear solvers because my colleague did the simulation at the National Institute of Standards and Technology. Randy McDermott, he was actually a PhD student here at the University of Utah. And so he is behind the software called the Fire Dynamics Simulator. That is the standard software that is used worldwide to investigate fire accidents. And it's tremendous work that they're doing at NIST. So I'll share this with you. It's about a 10-minute video, but I'll probably chop it halfway, stop it at 5 minutes. But I encourage you to watch it, and then I'll explain what's happening behind the scenes. Okay, so let's see. Oops.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, a fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic from Engine 26 of the San Francisco Fire Department. NIST examined the fire dynamics of this incident at the request and the San Francisco Fire Department.
On Zoom,
at 10:45 in the morning, a call was dispatched for a reported fire due to an electrical short. Engine 26 arrived on scene within 3 minutes of the dispatch and reported light smoke conditions. They made entry through the front door with 1 3/4-inch hose line. At approximately 10:54,
sorry, let me go back. Okay.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight.
Let me try something. I'm going to try to pipe my audio into the speaker system in the room. Let's see. Those on Zoom, you can watch on your internet browser.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in 2 line-of-duty deaths. On June 2, 2011, a fire in a multi-level residential structure claimed the life of a lieutenant and firefighter paramedic from Engine 26 of the San Francisco Fire Department. NIST examined the fire dynamics of this incident at the request of NIOSH and the San Francisco Fire Department.
Essentially what happened,
at 10:45 in the morning, a call was dispatched for a reported fire due to an electrical short. Engine 26 arrived on scene within 3 minutes of the dispatch and reported light smoke conditions. They made entry through the front door with 1 3/4-inch hose line. At approximately 10:54, about 6 minutes after the arrival of Engine 26, Battalion Chief 9 followed the Engine 26 hose line up the front stairs, into the front door, and then down the stairs to the first floor or street level of the house.
Huge advanced system.
Battalion Chief 9 had a face-to-face discussion with the victims.
I will encourage you to watch it at
During
home,
this discussion,
don't mind.
Engine 26
But the
confirms
idea
that
is
the
that,
fire is below them, and Battalion Chief 9 indicates that the attack will be made from the basement level on the B side.
Of what happened, they
The
ran
battalion chief exited the building.
calculations of how the fire might
Engine
have
26
spread
remained in
and what
position near the top of the
caused,
stairway leading into the
unfortunate
basement.
deaths of
This was the last communication
firefighters.
with the Engine 26
And the
crew
CFD
members
simulations
inside of the
ended up
structure.
showing that, because one
Within
of the doors
11
was
minutes
open
of
in the
Engine
basement,
26's arrival on
and
the
the
scene,
firefighters were
the
gonna-
large windows
imagine
that
there's
made
a
up
fire over
most
here,
of the
smoke
side
is
seawall
kinda
of the basement
moving.
level
You have
began
one
to
door open
fail
over
due
there.
to heat
There's
from the
oxygen
fire.
coming in and smoke
As the
kinda
windows
leaving,
broke,
and
fresh
bunch
air
of
mixed
firefighters
with
are
hot
standing over here.
fuel-rich
You open
gases
the
in the
other door,
basement,
you
which
create
increased the
a
heat
fresh
release rate of
supply
the fire.
oxygen coming down from over
The
there,
increase in
and it
heat
moved the
release rate
fire
resulted in
directly
the rapid
direction
failure of the 6
firefighters.
window
They
panels.
were
It took
exposed to
less than
very
2
high levels of
minutes
heat,
for all of the windows to fail.
and they lost their lives because of
After
that.
the
That's
rear
like if you
basement
ask me if you
windows
know a
began to
firefighter. My neighbor
self-vent,
is a firefighter.
Engine 24 and
And,
Rescue
you
1A
ask them,
tried to
this is
make
like,
entry
don't
through the
open any doors.
pedestrian
You
door in
gotta,
the garage
like,
to attack
they
the
have to
fire,
plan and
but they were
communicate
forced
correctly
back by
about it, but,
extreme heat and
unfortunately,
heavy
at
black
that-
smoke.
in that incident,
With
they
the
did not
pedestrian
communicate
door
properly.
between
And
the
so,
garage and the first floor hallway
the
open,
investigation
heavy black
showed
smoke
that,
began flowing out of the open.
The simulation, so the point is that I want to show you here is that they ran CFD calculations. So these are computational
Fire
fluid
gas,
dynamics
the center of the
calculations.
stairway, from the basement shows the pressure plane along the center
Showing
of the
how-
stairway,
so
from the
they ended
basement
up
to the laundry
opening
room
this
landing between the basement and the first floor. An estimate of the
yes, this
pressure
basement
increase
window
is shown
failed,
before
then
and after the first
firefighters were
basement
over
window
here,
failed.
and it ended up pushing all the
One of the
fire in
hazards to
that direction.
firefighters located in the exhaust portion of the flow path is convective heat transfer.
So this explains the whole thing. The video explains the whole thing.
And are
But
flowing
this
up the
method, where you're seeing these
well,
kind of
then splitting on the
colors
first
and
floor,
animations,
with
et
some of
cetera,
the flow
these are
continuing up
actual
another
fluid
stairwell to the
dynamics
open front door,
calculations, okay?
and the
this
rest of the hot
my
gas flow
active area
moving
of
out of the
research,
open
and,
pedestrian doorway through the garage.
NIST and
Notice
my
that
group,
the
we've
open
collaborated
basement
in the
windows
past
on the
and
rear of the
talked
house
about
serve as
improving,
bidirectional
simulation methods,
vents,
etc. But
with fire
all of
gases
these
exiting the
simulation
upper
methods,
portions and
they
air entering the
result
lower
in a
portions.
system of
While on the
linear
front side of the
equations
house,
that you have to
the
solve.
front door and the door
And
to the
so
garage are
my
unidirectional
idea here
vents,
is that
serving only
this is
as
a
an exhaust
motivating
for the
example
fire
that linear
gases.
system of equations,
There have been many
they're
previous
actual, they're
fire
realistic,
incidents
they're
in which
important,
changes
they
in the
can be
flow
used,
paths have had an adverse
to
impact on
understand and solve
firefighter and
complex
occupant safety.
mysteries and,
Fires
help us
with
improve
rapidly
our
developing or
response in
changing flow
firefighting, for
paths
example.
are a significant hazard to
I advise you
firefighters.
to watch the video
The development
at
of
home, where you can actually hear what the person is saying. I apologize about this. Oh, man. Okay, so I'm gonna get back to the to the slides. So the idea is that using computational fluid dynamics, we solve fluid and heat transfer equations, and the numerical solution of that, and you will see in a tangible example of how we start with a fluid or a heat transfer problem, and that leads us to a system of equations. By the end of the semester, you will be doing that. You will learn how to do that. In this chapter, we're going to solve the a heat transfer problem in a piece of material, and we'll show you how to solve that problem numerically. You have to solve a system of linear equations, okay? But to get there, we have to get a few things out of the way, okay? I like learning objectives. So each chapter has a bunch of learning objectives. This is a non-exhaustive list of the things you're going to learn. So this is a subset of what you will probably be learning in this chapter. You'll be able to define a linear equation, distinguish between a linear and nonlinear equations, identify a linear system of equations. It's kind of boring to just read from the slides, but kind of helps remind us of what we're going to learn. You'll be able to write a linear system of equations in matrix form. So from after this chapter, you're going to come out thinking every time you see a matrix, you're going to think of the matrix as, oh, matrix is nothing more than a fancy representation of a system of linear equations. That's all there is to a matrix, okay? A fancy representation of a system of linear equations, okay? Identify rows and columns in a matrix, identify some common types of matrices we deal with, dense, triangular, diagonal, sparse, tridiagonal, etc. Define what we mean by a sparse matrix, define the objectives of a linear solver. Why do we need a linear solver, okay? And define the two approaches or the two types of linear solvers, which are direct and iterative. Classify a linear system of equations and identify which methodology is better. So I give you a matrix, and then you say, okay, this matrix corresponds to a system of equations, but with this matrix, which method is better, direct or iterative? You'll be able to tell that. Use the TDMA, which is the tridiagonal matrix algorithm, which is a direct solution method to solve a tridiagonal system of equations. Those systems arise from heat transfer and fluid mechanics problems, okay? There's pentadiagonal, and there's even higher diagonal systems. So, those show up all the time in our work, in actual engineering and engineering science work. So these are very handy tools you're going to be learning. You will learn to do this by hand and using Python. You'll be able to build tridiagonal matrices in Python, write Python code to do the tridiagonal matrix algorithm, use Python code to solve for the temperature distribution in a one-dimensional piece of material. We can't do 2D right now. We need a little bit more work to get there. And identify when a system is not, what diagonal dominance is, and when it's not diagonally dominant, how to make it diagonally dominant. You'll see what that means. The idea behind iterative methods, and then finally write code for 3 iterative methods: Jacobi, Gauss, Seidel, and successive over relaxation. Okay, let's start. What is a linear equation? Okay, I'll give you the answer. A linear equation is simply an equation where the unknowns, the things that you are looking to find an answer for, okay, show up in a linear fashion. So in other words, they're not squared, they're not under a complex function like cosine, exponential, okay? So these are examples of linear equations where the unknown here is x, unknown is y, unknown is u. And nonlinear equations where unknown is x, this is x squared, so this is a nonlinear equation, a nonlinear equation, and nonlinear equation. Okay, so now let me ask you this. I have a marker on me, but suppose that we take this equation, ay equals c. The unknown is y, and a and c are parameters. What that means, they're input. They are brought in from measurements, from somewhere else. But this is the equation. In this equation, I'm solving for y. So what if you had a squared y equals square root of c? Is that still a linear equation? Yeah, why? Yeah. Then you can call a cubed, you can call it d, and square root of c, you can call it e. But y is the unknown you're looking for, right? Fundamentally, y is the unknown you're looking for, okay? Okay. Now, systems of linear equations are just that. You take a collection of linear equations with more than one unknown, so x, y, z, or x1, x2, x3, or t1, t2, t3, t4, t15, Each one of those has an equation where those unknowns show up linearly, okay? For example, 2x plus 3y plus 5 and 5x plus 3y plus 7. If you remember your math, these are 2 equations and 2 unknowns, so they are well defined. We have enough information to solve for x and y. You can solve this by hand, but that's a system of linear equations. You could have 2 billion equations like that. It's still a system of linear equations, okay? Now, why do we need those? Because, as you're studying engineering, and in science and engineering, systems of linear equations are going to be everywhere. And especially if you end up doing computing, if you're doing anything, that has to do with data processing, numerical methods, optimization, discretization, you're going to end up with systems of linear equations. So it's going to make sense to study them before we do anything in numerical methods. You're going to see linear equations in interpolation. We're going to see linear equations when we're solving nonlinear systems of equations. We're going to see linear equations when we're solving ODEs. And if we get to PDEs, you'll see also linear systems of equations in PDEs. They're everywhere, literally. So that's why we start teaching linear equations. Okay. So now I'm going to take an example from separations and show you how you can derive a system of linear equations. Now, in this course, again, remember, I'm not holding you accountable to find the system, to derive the physics. Generally, I'll give you the system of equations and tell you what it describes. Sometimes I go on tangents to explain a little bit more in depth of where the equations came from. But, you know, occasionally there are simple examples like this one where, yeah, you know, with just basic logic, you are able to derive a system of equations, or you're able to derive something yourself. So this is an example in separations. Essentially, what separations do, they take a mixture of compounds. In this case, we're going to take 3 compounds, A, B, and C. They're coming in at a mass flow rate of 10 kilograms per second. And what these WA, WB, WC are, they are essentially the mass fractions of the incoming stream. So what this is saying is that 20% of these 10 kilograms per second correspond to compound A, 60% correspond to compound B, and 20% correspond to compound C. Okay, so 2 kilograms per second correspond to compound A, 6 kilograms per second correspond to compound B, and 2 kilograms per second correspond to compound C. So in other words, the mass flow rate of component I is simply the mass fraction of I times the total mass flow rate. Okay. Now, in this separation system, it just happens that we are able to know so this compound goes through a process over here, another process over there, and it tries to separate the compound separate. So our objective is to look at the station 1 up there. 93% of the outcome is compound B. And over here, there's like 75% C and 25%, 26% A, 74% C. And, this is still like kind of crazy mixture, but, we might be interested in just collecting compound B using this separation process. The point is we can measure the percentages of these compounds at each of these locations. Your task is to find the mass flow rates at station 1, station 2, and station 3. Okay. We're going to try to do this together. Okay. First, I'll let you do it as a group. So I want you to develop just the equations for X1, X2, and X3. In other words, the flow rates at station 1, station 2, and station 3. I'll give you the first equation, right? Mass should be conserved, right? So whatever is coming in over here, the 10 kilograms per second, it's only going to go to X1, X2, and X3. So X1 plus X2 plus X3 is 10, right? That's your first equation. Now, think about your other equations, okay? You have 3 unknowns, so you need 3 equations. I gave you one of the equations, you need 2 more. Think about it. If you have the slides, the answer is on the next slide, but don't use that because you will not learn anything. This formula is very important, okay? This formula is very important. So think about what happens to the compound A, the flow rate of A that's coming in. How does it go? So what's the flow rate of A that's coming in? 0.2 times 10, right? So that's 2 kilograms per second. Where is that going to go? It's going to go to WA times X1 plus WA times X2 plus W, right? It's just mass conservation. Good job. Yeah, you got it. Just find the equations, don't solve them.
We're keeping the same amount of A, B, and C.
Yes, yes, it's conserved. Yeah, it has to be, there's no reaction, it has to be conserved. Yeah. Yep, exactly. Yes, thank you. Good point. I don't want to go into reactions and that kind of stuff, but yes, good point. Yes, Paula. And B and C. So they're not disappearing, they're not reacting. Each compound is going to be conserved. Yes. Why Team Kirby? Who is Kirby? Is that someone or? Oh, in a TV, what TV show?
It's called
Kirby. I'm not, look, I'm not that old, but, oh, okay. Okay, action platform. I'm sorry. I'm sorry that I don't know Kirby. I was busy putting the lectures together. All right, so now I know. All right, so let's see who you guys got it. Most of you got it. So who would like to participate in telling us how to get to an answer? There's a group there. Duck, 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 goose. You guys have made any progress? That's okay. That's okay. Soup, team soup. Michael. Okay. Okay. At least kind of the methodology of getting the equations. Okay. What about you guys? Team Jupiter Snakes.
For our equations, we got the x1 plus x2 plus x3.
Yeah.
And focusing on the total mass. And
Got it.
We focus on the different compounds. So
Got it.
Compound A, you say
Mhm.
it's 2 kilograms going in.
Mhm.
So if you multiply the concentrations times the strain and kind of
The mass fraction. Yeah. Yeah. Equal.
So
Yep.
like 0.04 times x1
Yes.
plus 0.54
Yes.
times x2 plus 0.2.
Yes. Correct. Thank you, Jupiter Snakes. So, you got the idea. And the idea is that the same way we have conserved the total mass of what's coming in and what's leaving by saying that 10 kilograms are coming in, that should be equal to x1 plus x2 plus x3. That's the mass that's distributed across the different separation columns. The same thing applies for each compound. Okay. So your colleague there said that, are there any reactions in these compounds? No, they're not changing, they're not disappearing. Compound A stays as compound A, compound B, and compound C, the same thing. So the mass of compound A, the mass flow rate compound B, mass flow rate of compound C are also conserved. Okay, so we apply the same thing. We pick compound B, compound A, for example. So you get, for compound A, you get 0.04 x1. So that's the flow rate at station 1. 0.54 times x2 flow rate at station 2 plus 0.26 times x3 is equal to 0.2 times 10, right? That's what's coming in for A. And same thing for B. Now you could have chosen C, right? But then you will notice that when you create that set of equations, only 3 of them are unique. So you can use any 3 of those equations. Okay, the 4th equation is just going to be a copy of one of the other equations. Okay. It just so happened that I used AB, total flow rate plus A and B. Okay. So now the point of this is not to teach you separations, but just to show you that, hey, if you just assign symbols to things, you can derive systems of equations, okay, yourself. But the next step I want to make is to show you that this form is actually not very amenable to mathematical manipulation because it's annoying. Imagine having to write this form every time or having to write 1,000 of these equations. It's very annoying and not productive, okay? Not efficient. I don't like inefficient things, okay? So the first step I'm going to make in this is to combine the numbers for x1, so 1, 0.04, 0.93, they all multiply x1, right? So that's a vector with numbers 1, 0.04, 0.93, multiplying x1, right? So that's 1 times x1, and then 0.04 times x1, 0.93 times x1. Same thing for the second variable. You have 1, 0.54, 0.24 times x2, and same thing for the third, and equal 10, 2, and 6, right? So now, I hope that you can see that this is the same system of equations we had before. That's 1 times x1 plus 1 times x2 plus 1 times x3 equal 10. 0.04 times x1 plus 0.54 times x2 plus 0.26 times x3 equal 2, and so on. Okay. I want to take this one more step. My objective here is to get it into a form that is cleaner. Okay. So I'm going to take this one more step. These are just vectors multiplying these scalars x1, x2, x3. Now I want to combine x1, x2, x3 into a vector of their own. And then what happens is this. So if I write x1, x2, x3 as a column vector, this column vector, then these other vectors, 1 and 0.4, 0.93, they combine into a matrix. Prove it to yourself. You just did matrix vector multiplication in the exam. The first equation is 1 times x1 plus 1 times x2 plus 1 times x3 equal 10. The second equation is 0.04 times x1, right? Plus 0.54 times x2 plus 0.26 times x3 equal 2, and so on. So from now on, every time you see a matrix, think of this matrix as corresponding to a system of linear equations. Whatever that system comes from, okay, in this case came from separations, but it helps to have a meaning for things rather than just saying, oh, it's a matrix. What is a matrix? What is it representing? It's a coefficient matrix. Who cares? It represents a system of linear equations. It's solving something. It's trying to solve something, okay? But you see how we made it from what I called an ugly system of linear equations into, I think, a more elegant way to represent a system of linear equations. Because now, this matrix, I can take it and rip it apart and study it and understand its properties and make judgment calls about how to solve it, you know, its eigenvalues, how fast can we solve it, is it solvable, et cetera, right? The system that we looked at before obfuscated that fact. So it hid that fact. We couldn't see this. Now there's an entire branch of mathematics that just talks about matrices and their properties, linear algebra. Okay? Okay? So now we call this matrix the coefficient matrix A. We typically use a bracket symbol around it, square brackets. We call this the solution vector. That's what you're trying to find the answer for. Okay? And we call this the right-hand side vector. So you will find that in my codes, I either use RHS for right-hand side or B, okay? Whichever. So we started with separations. We wrote these three equations. Now we're doing matrix vector equal a vector. And now we're going to switch to a cleaner notation. Still, we're going to just talk about systems. When we talk about linear systems from now on, we're going to write them as AX equal B. Matrix A, coefficient matrix A, you're solving for the solution unknown vector X, which is a vector of unknowns, okay, equal to a right-hand side. Okay. So our objective is to find X, right? That's the objective of solving a linear system of equations. Okay, so this might seem a little bit silly, but I like to go through it. Just to show you that it's not as complicated as, or to just kind of reinforce some ideas that you might have learned before this class. So how do we find X? We have a matrix times X equal B. Let's take an analogy with a single equation. If you had a scalar, so 2x equal 3, AX equal B, then you would simply say X is equal B over A, right? So if this is 2x equals 3, you would say X equals 3 over 2. Okay. So why can't we do the same with this guy? Ah, okay. Wow. Okay. I told you you're a tough bunch. We can't divide by a matrix, right? But what can we do with a matrix? Yes. And the word inverse, when applied to a scalar, it's 1 over, right? So the inverse of a matrix is actually the equivalent. It's as if you're dividing by that matrix, whatever that means. You cannot do division by a matrix. It's undefined. What do? You divide by each number in it. It just doesn't make sense. But if you take the inverse of the matrix, think of the inverse essentially, what is 2 to the power minus 1? It's 1 over 2, right? So A inverse, that's the equivalent of the operation of just solving for the unknown, okay? It's just simply in a higher dimensional space, okay? Okay, so now we have the matrix inverse, and now we can define the objective of linear solvers is to do one or more of the following. Either find the inverse of A, which is probably what you have learned in high school or other classes, right? Or find an approximation to the inverse of A. This is going to hint to iterative solvers. Or solve the system without explicitly computing the inverse. That's like Gaussian elimination, which is what you've learned, kind of solving it by hand. And the TDMA, the tridiagonal matrix algorithm, does that as well. Okay. But when you think about the theory of systems, linear systems of equations, or linear solvers, their objective is to take linear systems, either find the inverse, find an approximate for the inverse, or directly or approximately solve the system without finding the inverse. And we're going to learn about all of these options. Okay. Now we'll take a quick detour over here to actually show you how we're going to solve this using Python, because we need to figure out a way to find the inverse for simple systems like this: 3 equations, 3 unknowns, 10 equations, 10 unknowns. Just find the inverse and call it a day. Okay. We will learn, however, that as we go to much larger systems where you have millions of equations and millions of unknowns, don't compute the inverse. Probably take you a few years to compute an inverse. To store it is probably also, you got to buy Amazon Cloud or something. So we don't do that. But for simple systems, you compute the inverse. Okay, and we're going to show you how we do that in Python. You probably know, but that's okay. Then it'll be just a boring few minutes for you. The brute force solution is, the method you're probably familiar with, is to just directly find the inverse, multiply the inverse by the right-hand side, and that gives you the solution. Okay, so we're going to do this in Python, and I want you to grab linsolve activity 1.ipython notebook from the linear solvers module. Okay, so in Python, there are 2 ways to solve a system of equations directly. And those come from NumPy. There are other libraries that give you a linear solver direct solvers. That's fine. We're going to employ numpy.linalgebra. So there's 2 functions. There's one called solve, which internally finds the inverse and solves the system of equations. And there's one called inverse, which is you find the inverse and then you take the inverse and multiply it by the right-hand side. Okay, so I've given you the code over here. You'll pull up your Jupyter notebooks, and I want you to kind of try to implement these codes. Okay, so that you can you get your hands, your muscles to practice. Okay. I'll do the same over here, and I think I might have this already open. Go to Jupyter. Okay. Go to Google Drive. This. So it's kind of hard to do it without. There you go. Okay, so I'm going to bring the slides to this do next to you over here. If I can find my cursor. All right. Okay, there you go. Okay. All right. So essentially, just cannot type in the matrix, coefficient matrix. You'll notice that for very simple matrices like this, I just like to type in the matrix as a list of lists. So square brackets and then brackets, and just type it up the way it looks like. You know, you open the outer list on the outside, and then you put in the first list for the first row, second list for the second row, third list for the third row, and then define the right-hand side simply as a list. So call that a vector, and then declare your solution as solve A, comma B. So solve coefficient matrix with this right-hand side, and then print the solution. Okay, let's see what you've got. Most of you got it. Anyone struggling? Fairly easy. Okay, so let's see. You got 111 over here. You got 0.04, and then 0.54, and then 0.26, and then 0.93, 0.24, and 0.0, right? And for the right-hand side, we have 10, 2, and 6. Solve A, comma B. Now, if you're confused as to what the arguments of solve are, or what the arguments of any function are, you know, put your cursor right next to the parentheses over here. Okay, see my cursor? Put your cursor here and press Shift Tab. Shift Tab. So the button Shift and the button Tab on your keyboard. It's mind-blowing, right? And it gives you the signature of the function. Okay, solve A, comma B, solve a linear system, linear matrix equation, or system of linear equations. Now that's not enough. If you press it one more time, sorry, Shift Tab and then Shift Tab, it gives you the full documentation. So press it twice, Shift Tab, gives you the full documentation. Computes the exact solution X of the well-determined full rank linear matrix equation AX equal B. Okay, so that tells you what A is and what B is. So A is the matrix, coefficient matrix, B is the right-hand side. Okay, okay, perfect. So now let's solve it. Boom, we got an answer. I hope that's the answer you got too. Okay, the other way, using the inverse, is simply you declare, you know, I declare a variable called A inverse, and that's the inverse of A. Now, same thing for the documentation, Shift Tab, and it gives you the full documentation of the thing. Okay, so computes the inverse of a matrix. Given a square matrix A, return the matrix A inverse satisfying A dot A inverse is the identity. Okay, now you want to take that inverse and multiply it by the right-hand side vector. Okay, so that's a matrix vector multiplication. The way I like to do this is I type A inverse at B. I want to run this. Python does its magic, figures out the sizing and how it's going to do that product, and it does it correctly. Okay? That's the most direct brute force approach to solve a system of linear equations. You do this. When do you do this? You do it every time you're in doubt, when your system is small. You know, you got like 5, 7, 8, 10 equations. You do this and move on with your life. And that's it. We can close the chapter and move on. But we're going to talk about other more complicated things because you're going to be facing much more complicated systems in your career, hopefully. Maybe not by the time you graduate, but one day in your life, you might face it. You say, you know, I remember this crazy professor taught us about iterative solvers. So I'm going to pull up the slides. You know, hopefully you have them stored on your cloud or something. And so, you know, and they might be worth something at that time. Okay. All right. Okay, if I can find my cursor. Okay. Now let's generalize. Any system of linear equations may be written in matrix form, where you have a coefficient matrix, you have a vector multiplying a vector of unknowns equal to a vector of right-hand sides. Each row in this matrix corresponds to one of the equations. Okay? The coefficients on this matrix, the coefficients of this row, correspond to the coefficients of the equation. So look at the first equation on the left, a11x1 plus a12x2 plus dot 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 plus a1n xn equal b1. That's exactly what you have on the right. a11x1 plus a12x2, because that's the dot product of the row vector by the column vector, okay, equal to b1, and so on. Now, we have a nomenclature here where we have two indices, because the matrix is a two-dimensional beast, right? So it must have two indices. To find your way around it, you got to find what row you're at and what column you're at. That's one way to index it. So these indices that we have at the bottom, they designate your location in the matrix. So if I give you if I tell you aij is one of the coefficients in the matrix, that would indicate where that coefficient is located. And typically, the first index is the row, and the second index is the column. So A45 is the entry in row 4, column 5. Okay, A713 is the entry in row 7, column 13. A1n is the entry in row 1, column n. AMN is the entry in row m, column n. Okay. I never liked the aij notation because I and j, what the heck, right? I and j. Why didn't they call them ARC, a row column? So that's what I call them, ARC, because I deal with matrices every day in my life. Even my son now, my 4-year-old, knows about matrices. Okay, but I never got around to understanding this aij. It's annoying, so I call it ARC, a row column. All right. So if you like that, great. Okay. If you stick with aij, also great. But now you know kind of how to find your way around the matrix, okay, with this indexing notation. Okay. Now the last entry, AMN, is essentially telling you the size of this matrix. This matrix is an M by N matrix, M rows and N columns. Okay. Now, let me ask you this. For this system, for this matrix, for this system to be well posed, what that means is, can we find an answer for this system? Can we find a solution? For it to be well posed, there should be a relation between the number of rows and the number of columns. Yes. Why? Okay, so let's translate that into something less abstract. When the matrix, Tata. those are all true statements, but I want to translate it into something that is more digestible. What does it mean when the matrix is square? When the matrix is square, number of rows equal numbers of columns. Yes.
You have the same number of variables.
Yes, you have as many equations as there are unknowns. So therefore you can solve it, right? And therefore that means you can find the inverse, right? So the abstraction to matrix form might obfuscate some intuitive facts, but always try to express an idea in something in words. Like, what does it mean when m and n are equal? It means we have as many equations as there are unknowns. What that means is that it's a well-posed system. We can solve it. We can find the solution. Okay. So what you all said is correct. Okay. I'm just trying to kind of phrase things in different words. The mathematical way is to say, yes, m needs to be equal to n. The matrix needs to be square. The matrix needs to be invertible. But also that means that same number of equations as there are unknowns. Okay. I have a couple more minutes and I'll finish off with this. There are many types of matrices that you will encounter in life as a human being. Okay. The most common type is when the matrix is full of entries everywhere. All the entries are non-zero, or most of them are non-zero. We call that a dense matrix. That's the one on the upper left. The next one is an upper triangular matrix where all entries below the main diagonal are zero. We call that upper triangular. Lower triangular is the opposite of that. All entries above the main diagonal are zero. A diagonal matrix is one where all entries are zero except on the main diagonal. Identity matrix is a diagonal matrix where all the entries are one. And a banded matrix is one where some diagonals are not zero, but everything else is zero. So banded, okay? Just bands. They might not be next to each other, but you might have one over here. You might have one over there. Okay, typically they are symmetric. Okay, but these are kind of the common types of matrices that you will encounter. What now? Right? We know how to do this, right? So why do we can just kind of close this chapter and move on with numerical methods? Unfortunately, and fortunately for me, because I'm a nerd about these things, I really love kind of dealing with linear systems. That's not the entire story. So my message to you is, look, if you're dealing with a very small system of equations, say a dozen equations that you're going to solve once and move on, or even you're doing some kind of regression or some interpolation where you have like 5 equations or 7 equations, just use numpy.solve and move on. Okay, don't worry about anything I'm going to talk about in the rest of this chapter. Okay, now you will encounter cases like this as you do some undergraduate research, some basic elemental numerical methods calculations, even advanced. I mean, with regression, you're going to encounter even with nonlinear equations, systems of equations, you're going to encounter small systems of linear equations that are fine. Just use numpy.solve or inverse and move on with your life. Don't worry about anything. Okay. However, if you end up gravitating towards solving complex ordinary differential equations, systems of ordinary differential equations that occur in space, describe things in space, I'll give you an example in a minute, or partial differential equations, and add to that time dependence, then you are going to encounter very, very large systems of equations. And I'm not talking 1,000 equations or 10,000 equations. I'm talking on the order of millions of equations. So it's not uncommon for my group to be solving systems that are, about 1 billion equations with 1 billion unknowns. And doing that repetitively, all of the simulations you saw before for the orchestra early on, those were huge. Those were really large systems of equations, okay, in the order of tens of millions, okay? And we had to do that repetitively to track the motion of the air as it moved from one point over here to the door, for example. So we had to repetitively solve that system over and over and over again. And when you hit that level of complexity, then you might ask, okay, what's wrong with using solve? There's nothing wrong with that, except it is very expensive and inefficient. And you would be lucky to even be able to find a solution within probably a month time, or even if it gives you a solution at all. Okay, so to show this to you, I'm going to consider a small example without delving into details, just to kind of show you, come up with a system where us together right now, we're going to play around with the number of equations, okay, that we're solving, and then see the cost that we're going to be paying when using the direct solve method or the inverse method. Okay, what I'm displaying here is a simple heat transfer problem in a material. We're gonna in a next lecture, we're gonna dig very deep into this, understand what it means. But for now, trust me, I hope you're starting to trust me now. Have confidence that this problem over here, where you have some material that is being heated somewhere in the middle, and it's at a fixed temperature on the left and on the right. So think, for example, of you're grilling and you have your spatula or something. One end of it is on the grill, it's being heated. The other end is on the atmosphere, or like it's kind of, you put it like in the middle and it's being heated from the middle. So something like that. Clearly, as this is being heated, heat is going to transfer in the material depending on these temperatures, and it's going to give you a temperature distribution. Worry not about where this equation came from. You will learn it in heat transfer. And worry not about how this system of equations came from, okay? Where it came from and how it's built, okay? All that you need to know now is that numerically, we can solve this equation if we take this rod and splice it into little pieces, okay? And come up with an algebraic, with a linear equation for each of those points. And that system gives you this system of equations, okay? So the more points you put to describe the temperature, you could say, I want to describe the temperature here using 6 points. So you'd be solving for 6 temperature points. Clearly, that's kind of not very accurate. You might say, I want 2,000 points or 10,000 or 1,000,000 points, okay? The beautiful thing is that this matrix looks the same regardless of the number of points. It just expands and expands. The first point looks like this, the last point looks like that, and all the points in between look like this. There's 1, -2, -2, -2, -2, 1, and then there's 0, 1, 1, 1, 1, 1, and there's 1, and there's 0. Special type of matrix. We're going to dig very deep into it. However, now I want to show you that solving this system of equations, as you increase the number of equations, in other words, increase the number of points that you're solving for in that rod to get more temperature points, to get a more accurate solution, is going to start costing you, okay? So I want you to open up this LinSolve Activity 2. Direct solvers are expensive from the solvers module. And so go ahead and load it up. And together, there's code in there. All you need to change is going to be one number. And then you execute the notebook and see what happens. Okay? Some of you already started doing that, but bear with me for a moment. Okay, while I'll load this up. Okay. Let's see. All right. Oops. Okay. So this is solving. I hope you can see the board. Yep, yes, this is good. Okay, so there's a bunch of code over here. Don't worry about it. Go ahead and execute the first cell, Shift Enter. And it's going to give you this little star over here. So once the star is done, it means it's computed and it's solving this system of equations. All you need to do here is change this number. This number n is the number of equations. So 20 means 20 equations, 20 unknowns. Okay. And I promise you that that's going to describe the temperature distribution in that rod. Then go ahead and let's start with, let's say, 10 points. Okay. and just execute this cell. Okay, it executed it. Now I want to solve it. So whatever this code did, it built a coefficient matrix A, and it built a right-hand side B. And now I'm ready to solve it for T, my temperature. Okay, so I just put T equals solve AB, and I'm going to time it. Okay, I'm going to time it because we're going to look at how cost is going to increase as we increase the number of equations. So go ahead and execute this cell. It took me 0.023 seconds to do this. Let's see what some of the numbers you're getting. Different computers are going to give different numbers. Okay. Did you go ahead and execute? Perfect. Yep. And then execute the last cell. And you're going to see a beautiful color map showing the temperature. This is the color bar of temperature. So yellow is the hottest, and kind of dark purple is the lowest at 300 degrees. Okay. So clearly, this is where the heating source is, right? Temperature is at its peak over here, and it kind of slowly, gradually goes down. Okay. Now let's do it for, what, 40 equations. Go ahead. Do it for 40 equations. 40. Okay. Took 0.009 seconds. And now I have slightly better looking, even, a nice looking description of the temperature in that rod, right? Okay. It's still a reasonable number, 0.009 seconds. I still think it's expensive, but that's pretty reasonable, right? What numbers are you getting? Ballpark, similar numbers? Jake?
It did it the first.
Oh, gotcha, because you're formatting, it's truncating the printout. We can fix that. There's a little trick to set for NumPy to change the formatting. Okay. What numbers are you getting? Go ahead and play with the number of equations. Yeah. 0.08. Okay. So go ahead now. Pick another number of equations. Give me a number. 10,000. Okay. 10,000. So first, let's do maybe 1,000 just to see kind of how it looks like. So, okay, it took 0.05 seconds. And look at that, 1,000 equations. We have a more accurate representation, okay? Now let's go to 10,000. Who gave that crazy number? 10,000. Okay, look at it. Still executing, right? Still executing. I could go pick up my kids from daycare and come back. Okay, took 9 seconds. Okay, took 9 seconds. It killed her kernel. 6.6. Wow, yeah. What are you getting? Some of you, your computers are crashing, right? Your kernels are crashing. What are you getting? 5.3. Okay. Okay, you have, are you on the server or local? Local. Yeah, you have better computers than I have. All right, so let's maybe try, okay, what's another number we should try? 100,000. All right, add a 0. You're going to crash my kernel. All right, 100,000. What do you think it's going to take? Probably longer than we are willing to wait for, okay? So you want to, okay, hey, you know what? You do this as at home. I know you're trying to trick me to not do the lecture. I'm joking. I'm joking. I'm joking. Okay, so clearly, this is a problem, okay? Using this direct solve method is not the most efficient, is not the cheapest method. Look at that, kernel appears to have failed. Thank you so much. But actually, this is good that it caused it to crash. Okay, thank you. Okay, so it's a problem. It couldn't even solve it. It didn't even have enough memory to probably handle that big of a matrix. Okay, so that's a serious problem. I'm seeing like some mind-blowing things going on over there. Okay. There are many reasons for why this happens, and thankfully, we do have a solution for this, okay? We do have a solution for this. So what I'm going to show you here is, so I took this same problem, the heat transfer problem, and I solved it, and I timed the solution using both the inverse and the standard solver. So the inverse is shown in red, and the standard solver is shown in blue. And I plotted the time to solution, so that tick-tock time, how much time it's going to take to solve the problem, versus the number of equations. So as I increase the number of equations, you clearly see this rise. Okay, I say this is actually almost exponential rise in the cost to solve it in time. Okay, if you continue, it will start curving upwards. Okay, now what I'm showing in black is a method that I'm going to teach you next. Okay, that is much, much cheaper and scales linearly as you increase the number of equations. And it's actually several orders of magnitude cheaper than the standard method. So take the last point on the black line and compare it with the red point. So the red point is about 10 seconds versus the other one is 10 to the minus 2 seconds, 3 orders of magnitude. Okay, 3 orders of magnitude difference. Okay, so way cheaper. Okay, and this is only in 1 dimension. Now, if you go to 2 dimensions, this is again, plotting solution time versus number of equations. This is the cost of the direct solve method, and it just crashes. After that, just crashes, doesn't work anymore. These are some other techniques to solve this system of equations. We're going to talk about those briefly, okay? But this is the problem with these direct methods, okay? Direct methods are essentially exact methods. They have no errors in the solution beyond the round-off error, which occurs when you're multiplying and dividing numbers. Direct methods solve the system exactly. So they either find the A inverse or solve for the unknowns directly, like Gaussian elimination, right? Or find the A inverse. Both the same, 2 sides of the same coin. They are exact, but they're expensive. Okay, that's the price you pay for getting an exact solution. Okay, and there are another class of methods, which we'll also talk about, which are called iterative methods, which say, I don't want to solve this system exactly. I want to solve it approximately, because oftentimes I have more error in the modeling that led to the system of equations. So I don't have to, why do I need to solve the system of equations exactly? I have so much error that led to the formulas to develop the system of equations. Why worry about solving the system of equations exactly? Okay. Now, sticking with direct methods, it just so happens that some systems of equations have a certain unique structure for which there are very efficient direct methods. So we learn about only one efficient direct method called the tri-diagonal matrix algorithm. Do you want to guess where the word comes from? Tri-diagonal matrix. It's a matrix that has, yes, 3 diagonals. Thank you. Okay. So we will only learn, so we learned one direct method, which is, well, actually, we didn't learn it. We just learned how to use it in Python, right? The numpy.linearalgebra.solve and the inverse. Okay, those are 2 direct methods. They're almost identical. Just use them. Small systems of equations, it does a few dozen equations and, call it a day. But there's a class of systems called tri-diagonal systems for which there's a very efficient direct method. So you get the benefit of the direct method, which gives you an exact answer, and you get the benefit of efficiency and cheap cost. Okay, so this method is called tri-diagonal matrix algorithm, or TDMA. It's also known as the Thomas algorithm. So I will use those words interchangeably. So if I tell you use TDMA or use Thomas algorithm, it's the same thing. Okay. Now, this method applies to special kinds of matrices called the tridiagonal matrices, for which there's only 3 non-zero diagonals: the main diagonal, first upper diagonal, and first lower diagonal. Okay? Everything else is zeros everywhere. Okay? Now, what's so special about this matrix is that, well, actually, that's what we just solved. This kind of matrix shows up in diffusion type problems, okay? Like heat transfer, for example, or diffusion, mass diffusion, okay? So it's very common to encounter this kind of system in chemical and mechanical engineering, okay? So that's why we study it, and there's a very efficient technique to solve it, okay? Now, the beauty of this is that, well, because everything else in the matrix is zero except the 3 diagonals, we can save on storage by only storing the non-zero diagonals. So one of the reasons that some of our kernels crashed is that when we are doing, 10,000 equations, that's a matrix 10,000 by 10,000, right? 10,000 entries. But for the heat transfer problem, if you remember that matrix, most of the entries were zero, yet we stored everything in that matrix for nothing, right? Those zeros are insignificant. Okay? I mean, they matter in the solution, but really, we don't need to store them because we know they're zeros. So one of the benefits, and one of the other benefits of tridiagonal matrices is that we only need these 3 diagonals. We're going to call the main diagonal D, okay? Main diagonal, we call it D. The upper diagonal, we call it U. And the lower diagonal, we call it L. Now observe, here I'm indexing from 1, okay? So the main diagonal goes from 1 to n. It's just a vector, right? The main diagonal can be described as a vector that contains the entries D1, D2, D3, all the way to Dn. The upper diagonal, likewise, is a vector, but the size of this vector is n minus 1, right? Because it's shifted by 1 entry, right? Same thing for the lower diagonal, we call it L. The lower diagonal vector goes from L1 to Ln minus 1. Now, I'm just going to give you the formula for the tridiagonal matrix algorithm. In an exam, I will give you the formula. It's just an algorithm. We're not going to prove how it was obtained. That's not the purpose of this class. The purpose of this class is to take that formula and use it in a programming, and solve problems with it, and then compare it, for example, to a standard solution method, okay? So all you care about here are these 3 diagonals. So programmatically, when you think about the Thomas algorithm, what do you need to give the Thomas algorithm for it to give you a solution? You need the main diagonal, upper diagonal, lower diagonal, and the right-hand side. That's all you need, right? You can give it the matrix, but why worry about building a crazy matrix like this? Just build the diagonals as vectors, give them to the Thomas algorithm, and it will give you back a solution. Okay? Now, the formula for the Thomas algorithm is this. It's just an algorithm, a sequence of steps that you need to implement, given L, U, D, and B. So these are vectors, okay, row vectors, column, whatever you want to write them as. Okay, it doesn't matter. In Python, think of them as lists of numbers, okay? You have the lower diagonal L, upper diagonal U, main diagonal D, and the right-hand side vector B. The Thomas algorithm, or the TDMA algorithm, goes in 2 steps. First, you start with the main diagonal and the right-hand side. You take each entry in DI and you apply this formula. I'll show you in a minute how you can write this out for ease. You start at I equal 2 all the way to n. So we're indexing from 1 over here, okay? You start at I equal 2 all the way to n. Then you say, okay, D2 is equal, the new D2 is equal, the old D2 minus U1 times L1 over D1, okay? And then you go to B and say B2 is equal, new B2 is equal, old B2 minus B1 L1 over D1, and you repeat all the way to N, to the last entry. So what you've done, you're modifying the main diagonal, and you're modifying the right-hand side. And then you start from the end over here. You go find the last solution, the last answer, xn is bn over dn, and then you iterate backwards from n minus 1 to 1 with this formula. Xn minus 1 would be bn minus 1 minus un minus 1 xn over dn minus 1, and so on. Okay, this all seems like it's all far-fetched. Hence, the example is not an activity, it's just an example. I put it in the slides. Take those slides, rehearse this example at home, by hand. But you're not gonna, use it by hand, right? For any point in your life, okay? We're gonna use the code for it to solve very large systems, but it's good to kind of practice this indexing stuff and how it's working, okay? A note for those using slides, I know it might be annoying, but please grab the most recent version of the slides. Okay, I know you might have notes on your previous slot, from last week. Apologize for that, but I try to update the slides, because I got some fancy ideas before the lecture. So grab the most recent version. Okay. Okay, so this is a system of equations. When you look at it like this, it's ugly. It doesn't show any structure. Okay, it doesn't show any structure. It's only when you write it in matrix form that you see behind what you're seeing. And look at that. When I transform this system into a matrix form, I immediately realize, oh, this is a tridiagonal matrix. Main diagonal, first upper, first lower diagonal. Okay, so I know I can use the Thomas algorithm on it. No questions asked. You might have zeros on the diagonal, on one of the diagonals, okay? That might mess up with your solution, but as long as those three diagonals are non-zero, then you're good to go, okay? Now, here's how I would do it. I would first write the main diagonal, the lower diagonal, and the upper diagonal as vectors, okay? So the lower diagonal is 1, 4, 2, main diagonal 2, 2, minus 1, minus 1, and the upper diagonal is minus 3, minus 1, 1. And I would also write the right-hand side, minus 4, 2, 9, 2. Now, when you write it this way, you know that this is D1, D2, D3, D4. This is L1, L2, L3, U1, U2, U3. And this is B1, B2, B3, B4. Once you have those, then it's just a matter of a mechanistic procedure to implement to use the Thomas algorithm to find a solution. Okay, I'm not gonna go through the details, but just let's do like I equal 2. So that's the formula for step 1. You start with I equal 2. You take D2 and modify it. D2 is equal to D2 minus U1 L1 over D1. So therefore you get 2 minus, okay, what is D2? It's 2. What is U1? It's minus 3. What is L1? It's 1 over 2. It's kind of, just keeping track of all of those quantities, plugging them in and getting an answer. So that's D2 and that's B2. And you continue for I equal 3 and I equal 4. You get the new D2, D3, D4, B2, B3, B4. Your D1 is unmodified, okay? And then step 2, you implement the second formula. You start with the end, I equal 4. That's x4 equal b4 over d4. You take the ratio. Bam, you get your first solution, x4. Remember, we're looking for the x values. Those are our unknowns. Same thing, x3, x2, and x1, okay? Now, this system, I set it up in a way so that we get 1, 2, 3, 4 for the solution. Yes? Some off diagonal, no, you're done. Nope, you can't do it. That has to be strictly tridiagonal. Now, you get those in heat transfer problems all the time. 1D heat transfer, you get them all the time. In 2D heat transfer, you get what's called a pentadiagonal system. Okay, so you have two additional off diagonals. There's a pentadiagonal matrix algorithm, a bit more complicated than this, but it's also one way to do it. Okay. Yes. Correct. Because well, whatever you have in the denominator, you cannot have zeros in the main diagonal, because your colleague made an astute observation that on the main diagonal you cannot have zeros because you're always dividing by d over here. So if you have zero, your solution is going to blow up. But on the off diagonals, it's okay, right? U and L, it's okay because we're not dividing by those at all. Okay. Clearly, there are these sorts of restrictions, but only on the main diagonal. Okay. Okay. So now I'll ask you, what types of errors are present in the Thomas algorithm? Remember, at one point we spoke about the three types of errors encountered in numerical methods, right? Round off errors, truncation errors, and iteration errors. So consult with your groups